Okay, this is section 5.4. It's going to be about link layer addressing. That is, how do we address nodes, links, at the link layer. We talked about IP addresses a good bit already in our class. You remember that an IP address is a 32-bit number. We usually look at that as 4 8-bit numbers when we look at the decimal version of them. Remember that dotted decimal notation like 192.168.0.1. And we know that an IP address works at the network layer. What we're going to introduce today in this section is another address, a MAC address, Media Access Control address. This is basically the link layer address for a node. It's a 48-bit number. So the big question that we would like to be able to answer from understanding this slide is, why is it that a computer needs 2 addresses? Why is it that an interface needs 2 addresses? Okay, so every computer in this room has an IP address and a MAC address. Actually, every interface. So your computer probably has one for wired and wireless. What's the difference, right? You can see the question mark I've got there on function implies these 2 addresses kind of serve a different function, and therefore that's why 2 are needed. Remember, what's the use of what's the purpose for an IP address? It's used to get datagrams to the destination subnet, right? We use IP addresses to actually route datagrams, to route network layer packets from one subnet really to another subnet. The MAC address is really just, the function of it is to get a frame from one interface to another interface on the same network. This should make sense when we think about the difference between what the network layer does, which is go over multiple hops, route over multiple hops, versus what the link layer is about, is just getting a frame from point A to point B where those 2 points are adjacent nodes on a link. Those are the differences in the functions of these 2 addresses. They have some differences in the properties that are used to carry this out. An IP address is hierarchical. That is, everybody on this subnet has to have an address that starts with this network part, right? A MAC address is a flat space. What that means is you can have any address in the space. There's no real idea that this block of addresses is geographically in a different spot than this other block. Because of that, IP addresses are not portable. You can't have the same address here as you do if you're in New York. The IP address actually it definitely connotes, it explains, it's associated with your geographic and network location. Does that make sense? Whereas a MAC address is completely portable. When you go to New York, you will have to get a different IP address from some wireless network that you connect to up there. It'll have to be in their range of addresses. Your MAC address will stay the same, and in that sense it's portable. Your MAC address is burned into the ROM of your network interface card, and you're going to have the same MAC address whether you're here or in Africa.
So that happens like whenever the hardware is produced?
Right. The MAC address is actually administered, the allocation of MAC addresses is administered by the IEEE, which is this organization of electrical and electronics engineers. So a manufacturer, like I don't know who's the manufacturer of NICs, Samsung, is going to buy a chunk of MAC address space. So that's still like a range of addresses. They're going to start with the same digits. And then that way they can assure they're unique. They do have to be unique. Otherwise, if there were 2 people on the same network with the same MAC address, they would start getting each other's frames. Yeah. So it has to be unique, and that's the way uniqueness is enforced, is that the manufacturers buy chunks of addresses. But you can take your Samsung address and be intermixed and mingle with Texas Instruments, NICs, and their address range.
Isn't it written in hex?
Right. They usually put those 48 bits in hex. That's 48 divided by 8, 6. So that would be 6 hex digits will represent those. No, hex can represent 4 bits. So 48 divided by 4 is 12. So a 12-digit hex number represents a MAC address.
Okay, but this would be, there's 2 to the 48 addresses.
Mm-hmm.
So they're not,
I think if you work the math on that, what is 2 to the 48? It's a lot more. I don't think we're in danger of running out of MAC address space. This is exponential, right? The difference between 32 and 48 is 16.
It's 2.8 times 10 to the 14th.
2.8 times 10 to the 14th different addresses. Yeah. And how many people are there on Earth? 6, 7 billion. And how many? Well, a billion is 10 to the 9th.
So you got a trillion plus another 2, so 1,000 trillion.
Does that let everybody have 10 MAC addresses? I forgot what number you said. What number did you say?
It's 2.8 times 10 to the 14th, and we have 7 times 10 to the 9 people on Earth. So that would turn out to be.
There's a order of magnitude of 5 difference there.
Right.
So that's about.
But you're going to lose 1 because it's 2 divided by 7, so it'd be 10 to the 4.
10 to the 4 is 10,000, right?
Yeah.
So we're probably in good shape there.
So each one does 1 device, correct?
Right. Or really one interface.
Or
one interface.
Each device has 1 MAC address.
Each interface has a MAC address. So your wireless card would have a MAC address and an IP address. Your hardwire Ethernet would have a MAC address and an IP address.
So what about for stuff that like a cell phone that has a wireless card and a network card, that would have 2 MAC addresses?
You would definitely have to have a MAC address for the wireless, and I'm not sure how the 3G, 4G would work. There would be something analogous to a MAC address, but it might not actually be a MAC address. And this MAC is kind of associated with Ethernet. Ethernet and wireless are kind of compatible. It would have a different link layer, so it would have a different link layer address. Is that other questions on this? If you open up your terminal and type in ipconfig in Windows or ifconfig in Mac or Linux, you can see the information about your interfaces, and you can see your MAC address and your IP address and a bunch of other stuff for that matter. You might want to go ahead and do that if you want. That's a pretty important command to know if you're ever going to troubleshoot network stuff.
Isn't that but since your MAC address is unique, you don't want outside people knowing about it, right? Because that could open you up to possible.
Well, the thing is, somebody on an outside network couldn't send packets, couldn't send frames to your MAC address unless you're on the same network. Because that's really the sphere of knowledge for MAC addresses is the same network.
What if they knew the network I was on? But they would have to be on.
Or they would have to send it from a computer that's on the same network as you. When you broadcast, we're going to talk about this in a second, but when you broadcast, or even when you send a message to a MAC address, everybody listens to it and would hear it, and if it's addressed to you, then you would accept it. If it's not, then you just ignore it. So if you send a frame to a MAC address that was not on that network, it would just be ignored by everybody and completely dropped.
I've seen online when people post pictures network configuration stuff, and they always blur out the MAC address.
I mean, it could be kind of more sensitive because it is unique and it uniquely kind of identifies you. I don't know if there are severe security implications from that. I'm not sure what they are, but I respect that, and I wouldn't want to give that number out either. The book has this analogy to say it's sort of like the way a street address A street address is like an IP address. It's portable. It's hierarchical. It says where you live on this earth, right? Whereas a social security number is very flat and it's portable, right? Just because you have a social security number that's one digit away from your brother doesn't mean that you guys live next to each other anymore, necessarily. Okay. Yeah.
I'm probably asking too many questions, but
No.
So would MAC addresses get retired and then reused?
I don't know the process on that,
my
but
phone, that MAC address has been used. So
I don't think that. But see, the manufacturers wouldn't know that. They might know when they had assigned it, but if they can't know for sure that MAC address still isn't being used, then I don't think they could reuse that address. But I mean, if you've got that many, then I think it's not a huge deal.
Eventually, you're going to run out of it.
Well, probably before we get to that number, they probably figure out a better way to do stuff.
I mean, if we got a new link layer, we could set it up to have a whole new address space. But everybody's always wanted backwards compatibility with Ethernet because that kind of has become the dominant standard. So if you want to work on an Ethernet network, you got to use this structure. Even though we went from 10 megabit Ethernet to 100 to 1,000 gigabit Ethernet and even 10 gigabit Ethernet, but they all use the same frame format, which has 48-bit addresses. Okay, so this is an example of what LAN addresses look like, where the MAC addresses are listed in hex. You know, a hex digit is a number between 0 and the letter F, representing 0 to 15. Every LAN adapter has this unique LAN address, which is the MAC address. They reserve all ones, which is all Fs, to be the broadcast address. So if you want to send a frame to every adapter, every NIC on your subnet, your LAN, you can broadcast it by sending it to that address, and everyone will receive the packet and process it. And sometimes you need to do that for certain kinds of messages. Like if you're trying to find somebody who, trying to find an IP address of somebody who you don't know their IP address of.
So everyone on that LAN will get that message.
Right. Okay, let's talk about a kind of helper protocol for Ethernet. It's called the Address Resolution Protocol, ARP. This is a problem that comes up in this situation. Since we have two types of addresses, IP addresses and MAC addresses, there will be situations where we know the IP address of somebody, but we don't know their MAC address. So imagine that we are trying to find well, you can see what's listed on here. We have the IP address on top and the MAC address on bottom. Okay, how do we determine the MAC address of? Are these labeled? Well, one of these, if we know its IP address. ARP solves this problem. It answers this question. And basically, it's going to map IP addresses and MAC addresses. It's going to map IP addresses to MAC addresses. So the ARP table has these three things. Right? So the ARP table exists in Ethernet or LAN nodes. And you can imagine this table has a bunch of rows, and every row has three things in it. It has an IP address, it has the MAC address of the computer with that IP address, and it has a time to live. Where the time to live is something, typically it's like 20 minutes. After that much time, this mapping will be forgotten. Okay, what's the point of that? What does that solve? What does that allow for the network? Yes, it allows these mappings to change over time, right? If you renewed your IP address and you got a new IP address from the DHCP server, your MAC address is still the same, but now there's a new mapping between IP address and MAC address. So after 20 minutes, that old entry would be removed from the table. I guess for some period of time, there should be 2 rows in the table with your old IP address and your new IP address. One of them is going to be wrong. I guess this system will learn what the correct mappings as it hears how people respond. All right, here is how ARP works for hosts within the same network. Let's say A wants to send a datagram, right, an IP datagram to B, and B's MAC address is not in A's ARP table. Okay, right, A sending to B, B's MAC address is not known. First step, A is going to broadcast an ARP query packet to its whole network. Remember, that's by setting the address to all ones, all F's. Everybody receives the ARP query. Everybody gets it. Inside the query, it has, as the contents of the packet, the address, the IP address that it wants the MAC address for. Yeah? Okay. B will receive that. It will realize, hey, I have that IP address. I need to respond to this. And it will unicast its MAC address back to A. Now, unicast, that means, this is the second to last step here, it means it's sending it directly to B because it knows B's MAC address.
And B sends to A.
B sends to A. B sends directly to A and only to A. It knows B's MAC address because it received this query from B's MAC address. Because in every packet there's a source MAC address and destination MAC address. The source MAC address, sorry, from A, the source in this packet, the broadcast packet, was A's MAC address. The destination was all ones. When B responds, it sends from itself, which it knows its own MAC address, and it sends the message to A. And it knows A's MAC address from the broadcast. When A receives that, it will cache the MAC address of B. Basically, it's going to save it to the table. So A is going to save the IP to MAC address pair in its ARP table, along with some timeout time when that information will expire. So this is what's called soft state. It's information that goes away unless it's refreshed. The cool thing about ARP is that it's completely plug and play. That is, it's self-learning. You just connect them up. At first, you may have a lot of these queries going out where people are saying, hey, who has this IP address? Everybody. As the answers come back, the system learns where things are.
So whenever B sends directly the unicast to A, how does it get back to A? It's using the IP or the MAC?
It's using the MAC. These two computers are on the same LAN, so that means they can talk to each other directly without any kind of network layer because they don't have to go through a router. They can talk directly to each other over the link layer.
Since they don't have the network layer, that's going to speed it up. So it's not wasting that overhead.
Yeah, you might see it that way. They still have to have some payload in the packet, but they don't. It doesn't have to be a whole IP datagram. Because really, ARP is kind of like right on top of the link layer. ARP really is kind of a glue that connects the link layer to the network layer, IP specifically. I believe I have a picture of this. So hopefully this makes sense. I have IP addresses, which are, you see in the A subnet, everything begins with a bunch of ones. In the B subnet, everything begins with a bunch of twos. And then, yeah, the router is on both subnets because it connects them. So it has to have multiple IP addresses and multiple MAC addresses, right? Because we have addresses per interface. So if we were going to walk through this, we want to send a datagram from A to B. And you see the IP addresses here, and the MAC addresses here and here. All right, so this is a more complex scenario than we just went through because we have a router in between. We're trying to send to a different network entirely. the two hosts are not on the same LAN. There's a router in between. So if I could try to sum this up ahead of time, we're not going to get responses straight from B because B and A are not directly connected to each other on the same link. Does that make sense? So somebody's going to have to answer our queries on behalf of B. And who is that going to be? The router, right? So it's sort of like the router is going to have to, I would say, impersonate the MAC addresses on the other subnet to make sure that the hosts over here know how to get to them. And basically, the hosts over here are going to think that the MAC address for B is the MAC address of the router. So that anything that's destined to go to B really is going to have to go to this interface on the router. Even though it's not addressed to this IP address, all these ones and 110, it is going to go to this MAC address.
So the router will also contain an ARP table?
Right. It'll actually contain ARP tables for both sides.
But so then will A and B each have their own ARP table as well? So
Mm-hmm.
there will be 4 ARP tables in this case.
Mm-hmm.
A, router, B.
Mm-hmm. I mean, I guess you could see the router could just have one.
So there's an ARP table per interface as well?
Mm-hmm. I don't know. Let's see. I guess you could get by if. I mean, none of these. The router has multiple interfaces. I guess you could just do it with one, and then it would be smarter, right? Because you'd know, hey, if I need to send to this, it would make sense that your wired and wireless adapters, if they could share the ARP table, which an ARP table is something that's in software, you can see the ARP stuff. Look, you can use commands and see the ARP table in your computer. If the wireless interface has already discovered a lot of mappings, it would be a waste for the wired to have to rediscover them all. Okay, so should we walk through this, or was that discussion enough? Want to walk?
Let's walk.
Let's walk. All right. So we've got. You could still think about it as 2 ARP tables. This is what my notes have: 2 ARP tables in router R, one for each IP network. So A is going to create a datagram with the source IP address for A and the destination IP address for B. Right? We know what the IP addresses look like. Those are the dotted decimals. A is going to use ARP to get R's MAC address for this interface that has 110. So it's going to say who has the IP address 222, if I can just distinguish based on the last digit. And the router is going to say, oh, I have that because I know that I'm connected to that network, and I know that IP address is on the other side of this router. So R is going to respond on behalf of B and say, hey, you're looking for 222, A. You need to send to this MAC address, this E6E900. All right, so A gets that back, and A is going to create a link layer frame with R's MAC address as the destination, but the IP address will still be from A to B. All right, so in that case, the IP address source destination is not exactly the same as the MAC address source destination. Yeah? All right, so then R receives that. A's frame, A is going to send the frame. R is going to receive the frame. R is going to remove the datagram from the Ethernet frame. It's going to decapsulate it, see which interface it's supposed to forward this datagram to. Remember all that stuff we talked about last chapter? It's going to see that it's destined for B. And then if we're assuming here R doesn't know anything, R is going to have to use ARP again to figure out the MAC address for this IP address, the 222. So it'll broadcast who has MAC address for IP address 222. B will respond and say, hey, this is my MAC address, that's me. And then R will create a frame containing its MAC address on this side as the source, B's MAC address as the destination, but the source, let's see, what's going to be its IP source and destination? B will definitely be the destination. Will A or R be in the source? The source IP address. A is right. Because from B's perspective, it's going to have to know who's it talking to. And it doesn't want to talk to the router if it has to send something back. It's going to have to send, it's going to have to know the original source. So that's still going to be A. It's a little bit complicated, but that's the way of things. What is this? What questions do you have on this scenario? Basically, because the two LANs were separated by a router, we were on two separate LANs instead of the same, we have to run ARP for every LAN, and the router is going to kind of act on behalf of one party or the other party in the middle to connect those LANs. All right, another important thing to note here is that as the longer this runs, once your ARP table gets built up, right, you're going to remember this, and then you don't have to go through all this every time. You can just look it up in your ARP table, and it's probably there after the first time. Any questions on ARP? Remember, ARP stands for Address Resolution Protocol, and ARP should remind us of something from another layer. What does this remind you of?
IP tables.
Specifically, you remember another protocol that worked to do this same kind of process? Mapping from something to something?
Yeah,
it's pretty important. You got this. 3 letters.
Yeah, was it TCP? No, that was... Hold on. We talked about it for like 2 days.
We mapped names to IP addresses to sort of connect the application layer and the DNS. So you see how this is kind of sort of DNS all over again, but at a lower level. But it's designed differently in that it's a lot smaller scale, so we didn't need that hierarchical distributed database. We can kind of do it all and store it all locally. Okay, this is ARP.